Once again, I welcome everyone to this new video where I explain the chapter Classification of Elements and Periodicity in Properties from CBSE Class 11. Before few centuries, we people have only identified about 31 elements and we have been studying about those elements individually. But as decade passed, we came to know about many elements. Currently, there were about 118 elements. Now it is very difficult to study about all those 118 elements individually. To solve this problem, their similarities was taken into account and periodic table was introduced. At first, it was not same as that we see today. First, let us look the path that led to the development of modern periodic table. The German chemist John Dobreiner in early 18th century was the first to consider the idea of trends among properties of elements. By 1829, he proposed the law of triads that stated that the middle element of each of the triad had an atomic weight about the halfway between the atomic weight of other two. Also, the properties of middle element was between those other two elements. But this model had a drawback as it is not applicable for all the elements. The English chemist John Alexander Newland in 1865 propounded the law of octaves. He arranged the elements in increasing order of their atomic weights and noted that every eighth element had properties similar to the first element. This was similar to the music notes such as sa, re, ga, ma, where the first sound sa sound for every eighth elements. But this was also not the perfect way to classify elements as this rule was only true up to calcium. Later, Lothar Meyer and Mendeleev arranged the elements according to their atomic weight. While Dobreiner initiated the study of periodic relationship, it was Mendeleev who was responsible for publishing the periodic law for the first time, which stated that the properties of the elements are a periodic function of their atomic weights. Mendeleev's classification of elements were more elaborate than that of Meyer's. The boldness of Mendeleev's quantitative prediction led to the success of his periodic table. For example, the elements like gallium and germanium were unknown at the time of Mendeleev published his periodic table. He left a gap under aluminium and a gap under silicon and called these elements Eka aluminium and Eka silicon. But the only mistake done by Mendeleev was that he classified elements on the basis of atomic weights and faced a few confusion due to that. Whereas in modern periodic table, the elements were classified on the basis of atomic number or the number of protons in an element. But more than that, during his time, people doesn't know about subatomic particles and due to that he was almost correct. While undergoing many experiments such as X-ray spectra of elements, it is proved that atomic number is a more fundamental property of an element than its atomic mass. Therefore, Mendeleev's periodic law is then modified into modern periodic law, which states that the physical and chemical properties of the elements are periodic function of their atomic number. This was an important turning point in the study of inorganic chemistry. Also, it is now easy to visualize that as electronic configuration of element change, physical and chemical properties to change. In the long form periodic table, the horizontal rows are called periods and the vertical columns are called groups. There are altogether 7 periods. The period number corresponds to the highest principal quantum number of the elements in their period. The first period contains 2 elements. The subsequent periods consist of 8, 8, 18, 18 and 32 elements respectively. 14 elements of the both 6th and 7th period are placed in separate panel at the bottom. The naming of electron also faced many controversy. For example, even before the identification of the element with atomic number 104, the American claimed its name as Rutherfordium and the Soviets named it Kurchatovium. So to avoid such confusion, the IUPAC has made recommendation that until a new element's discovery is proved and its name is officially recognized, a new systematic nomenclature can be derived from it. Atomic number should be used. The distribution of electrons into orbitals of an atom is called its electronic configuration. The elements' location in the periodic table reflect the quantum number of the last orbitals. Now let us look some direct connection between the electronic configuration of the elements and the long-form periodic table. Elements in successive period of periodic table is associated with filling of the next higher principal energy level. In simple words, all the elements in a period have same n values at the valence shell. For example, the value of n in first period is 1 and for second it is 2, and this trend continues till the last period. In another way, we can also predict the period of that element by its valence shell. If the valence shell of the element is k, then it belongs to first period. You may have noticed before that 4p orbital is filled, 3d orbitals is filled. The element that contains d orbit in its valence shell belongs to the transition series. The element that contains f orbital in its valence shell belongs to inner transition series. Those which have 4s at the outermost shell is called lantanoid, and the elements of 7th period of inner transition series are called as actinoids. One thing you have to keep in mind is that when I say d or f orbital, it only means those elements which involve in filling of those electrons. Elements in the same vertical column or group have similar valence shell electronic configuration and similar properties. For example, group 1 elements, which is also called as alkali metals, have ns1 valence shell electronic configuration. On the basis of Aufbau principle and electronic configuration, we can classify elements into 4 blocks. They are S block, P block, D block and F block. When placing elements into blocks, we face 2 exceptions. 1. Helium although belongs to S block, but it is placed in F block as it is a noble gas. 2. Hydrogen show the character of both alkali metal and halogen, and still there are few confusion in placement of hydrogen atom. Now let us briefly see the salient features of this block. The S block elements. The elements of the group 1 and group 2, which have ns1 and ns2 outermost electronic configuration, belongs to the S block elements. They all are reactive metals with low ionization enthalpies. The metallic character and reactivity increases as we go down the group. They lose electrons to form 1 plus ion or 2 plus ion. Because of high reactivity, they are never found pure in nature. The compounds of the S block elements, with the exception of those of lithium and beryllium, are predominantly ionic. The P block elements comprise those belonging to group 13 to 18, and these together with S block elements are called representative elements or main group elements. The outermost electronic configuration varies from ns to np1 to ns to np6 in each period. At the end of each period is a noble gas element with a closed valence shell, ns to np6 configuration. All the orbitals in the valence shell of the noble gases are completely filled by electrons, and it is very difficult to alter this stable arrangement by addition or removal of electrons. The noble gas thus exhibit very low chemical reactivity. Preceding the noble gas family are 2 chemically important groups of non-metals. They are halogens and chalcogens, which have high negative electron gain enthalpies and readily add 1 or 2 electrons respectively to attain the stable noble gas configuration. The non-metallic character increases as we move from left to right across the period, and metallic character increases as we go down the group. D block element. The element of group 3 to 12 in the center of periodic table, which is characterized by the filling of inner d orbitals by electrons, are referred as D block elements. These elements have general electronic configuration n-1d 1 to 10, ns0 to 2. They are all metals. They mostly form colored ions, exhibit variable oxidation state, paramagnetism, and often used as catalyst. However, zinc, cadmium and mercury, which have electronic configuration n-1d 10, ns2, do not show most of the properties of transition element. They form a bridge between the chemically active metals of S block elements and the less active elements of group 13 and 14, and thus they are named as transition elements. The 2 rows of elements at the bottom of the periodic table, which consist of lantanoids and actinoids, belongs to F block. They have n-2 F 1 to 14, n-1d 0 to 1, ns2 electronic configuration. The last electron added to each element is filled in F bar orbital. These two series of elements are hence called the inner transition elements. They are all metals. Within each series, the properties of elements are quite similar. The chemistry of early actinoids is more complicated than the corresponding lanthanoids due to large number of oxidation states possible for these actinoids elements. Actinoids elements are radioactive. Most of the actinoids elements have been made only in nanogram quantities or even less by nuclear reaction, and their chemistry is not fully studied. The elements after uranium are called transuranium element. The elements are also been classified based on their metallic and non-metallic properties. Metal comprise more than 78% of all known elements and appear on the left side of the periodic table. In contrast, non-metals are located at the top right hand side of the periodic table. We can notice that in horizontal row, the properties of elements change from metallic on the left to non-metallic on the right. The elements such as germanium, arsenic show the property of both metals and non-metals, and these elements are called as semi-metals or metalloids. There are a lot of trends in physical properties of elements. Now let us look at some of them. There is no practical way by which the size of an individual atom can be measured. However, an estimate of the atomic size can be made by knowing the distance between the atoms in the combined state. One practical approach to estimate the size of an atom of a non-metallic element is to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule. And from this, the value of covalent radius of the element can be calculated. For example, the bond distance in chlorine molecule is 198 picometer, and half of this distance is 99 picometer is taken as the atomic radius of chlorine. The half of internuclear distance separating the metal core in the metallic crystal is called a metallic radius. For example, the distance between two adjacent copper atoms in solid copper is 256 picometer. Hence, the metallic radius of copper is assigned a value of 128 picometer. They are measured by X-ray or other spectroscopic methods, and for simplicity, they are called as atomic radius. The atomic size generally decreases across the period, as within a period the outer electrons are in the same valence shell and the effective nuclear charge increases as the atomic number increases, resulting in increased attraction of elements to nucleus. The atomic radius increases down the group because of the increase in the principal quantum number and the increase of distance between valence electron and nucleus. As noble gases are monoatomic, their radius is uptrained to van der Waals radii. The ionic radius can be estimated by measuring the distance between cations and anions in ionic crystals. In general, the ionic radii of elements exhibit the same trend as the atomic radii. A cation is smaller than its parent atom because it has fewer electrons while its nuclear charge remains the same. The size of the anion will be larger than that of parent atom because the addition of one or more electrons would result in the increase of repulsion among the electrons. For example, the ionic radius of fluoride ion is 136 picometer, whereas its atomic radius is only 64 picometer. On the other hand, the ionic radius of sodium is 186 picometer compared to the ionic radius of 95 picometer for sodium. The atoms and ions which contains the same number of electrons is called as isoelectronic species. For example, O2 minus ion, F minus ion, Na plus ion and Mg2 plus ion have 10 electrons each. The cation with greater positive charge will have smaller radius because of the greater attraction of electrons to nucleus. Anion with the greater negative charge will have the larger radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and ion will expand in size. A quantitative measure of the tendency of an electron to lose electron is given by its ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atom in its ground state. The ionization enthalpy is expressed in unit kilojoule per mole. Energy is always required to remove electron from an atom, and hence ionization enthalpies are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from a positively charged ion than from a neutral atom. Generally, ionization enthalpy increases as we go across a period and decreases as we descend in a group. The effective nuclear charge experienced by a valence electron in an atom will be less than the actual charge on the nucleus because of shielding or screening of the valence electron from the nucleus by the intervening core electrons. For example, the 2s electron in lithium is shielded from the nucleus by the inner core of 1s electrons. As a result, the valence electron experiences a net positive charge, which is less than the actual charge of positive 3. In general, shielding is effective when the orbitals in the inner cells are completely filled. This situation occurs in the case of alkali metals which have single outermost ns electron preceded by a noble gas electronic configuration. When we move across a period, successive electrons are added to orbitals in the same principal quantum level, and the shielding of nuclear charge by the inner electrons does not increase very much to compensate for the increased attraction of the electrons to the nucleus. Thus, across the period, increasing nuclear charge outweighs the shielding. As we go down the group, the distance from outermost electron and nucleus increases, and there is an increased shielding of nuclear charge by the electron at the inner level. In this case, increasing in shielding outweighs the increasing nuclear charge, and the removal of the outermost electron requires less energy down the group. When we consider same principal quantum level, an s electron is attracted to the nucleus more than a p electron, the penetration of a 2s electron to the nucleus is more than that of a 2p electron. Therefore, 2p electron is more shielded from the nucleus by the inner core of electron than the 2s electrons. As a result, the first ionization enthalpy of boron is slightly less than that of beryllium. Another anomaly is the smaller first ionization enthalpy of oxygen compared to the nitrogen. This arises because in nitrogen atom, 3 2p electrons reside in different atomic orbitals, whereas in the oxygen atom, 2 of the 4 2p electrons must occupy the same 2p orbitals, resulting in an increased electron-electron repulsion. Consequently, it is easier to remove the 4th 2p electron from oxygen than it is to remove one from those 2p electrons from nitrogen. When an electron is added to a neutral gaseous atom to convert it into a negative ion, the enthalpy change accompanying the process is defined as electron gain enthalpy. Depending on the element, the process of adding an electron to the atom can be either endothermic or exothermic. For many elements, energy is released when an electron is added to the atom, and the electron gain enthalpy is negative. For example, group 17 elements have very high negative electron gain enthalpies because they can attain stable noble gas electronic configuration by picking up an electron. On the other hand, noble gases have large positive electron gain enthalpies because the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. The electron gain enthalpy becomes more negative with increase in atomic number across a period. The effective nuclear charge increases from left to right across a period, and consequently it will be easier to add an electron to a smaller atom. Since the added electron on an average would be closer to the positively charged nucleus, as we move down a group, the electron gain enthalpy becomes less negative as the size of the atom increases and the added electron will be further from the nucleus. Due to high electron-electron repulsion N2 quantum level than that of other quantum level, the electron gain enthalpy of oxygen or fluorine is less negative than the succeeding elements. A qualitative measure of the ability of an atom in a chemical compound to attract saved electron to itself is called electronegativity. It is not a measurable quantity, but is thus provide a means of predicting the nature of force that holds a pair of atoms together. However, a number of numerical scales of electronegativity of elements such as Pauling scale, Millikan-Jaffe scale, Aldred-Roste scale have been developed. Among these, the Pauling scale developed by American scientist Linus Pauling is widely used. In 1922, it is assigned arbitrarily a value of 4.04 fluorine, which is considered to have greater stability to attract electrons. Electronegativity generally increases across a period from left to right and decreases down the group in periodic table. The attraction between the outer electrons and the nucleus increases as the atomic radius decreases in a period. On the same account, electronegativity values decreases with the increase in atomic radii down a group, which is similar to ionization enthalpies. The increase of electronegativity across a period is accompanied by an increase of non-metallic property or decrease in metallic properties of elements. Similarly, the decrease in electronegativity down a group is accompanied by a decrease in non-metallic properties or increase in metallic properties of elements. Now let us see the periodic trends in chemical properties such as periodicity of valence or oxidation state and anomalous properties of second period elements. The valence of representative element is usually equal to the number of electrons in the outermost orbitals or equal to 8 minus the number of outermost electrons. Now let us take two compounds which contains oxygen fluoride and Na2O. Among these three elements which formed these compounds, fluorine has the highest electronegativity compared to oxygen and sodium, and sodium has the least electronegativity compared to oxygen, and therefore when each of the atoms of fluorine shares one electron with oxygen in the OF2 molecules, being highest electronegative element, fluorine is given oxidation state -1. As there are two fluorine atoms, oxygen shares 2 electrons with the fluorine and thereby exhibit oxidation state +2. In Na2O, oxygen being more electronegative accepts 2 electrons, one from each of the two sodium atoms, so oxidation state -2, and sodium so +1 oxidation state as it loses 1 electron to oxygen. Thus, the oxidation state of an element in particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from other atoms in the molecule. Lithium, beryllium and the first element of group 13 to 17 differ in many respects of other members of their respective group. For example, lithium, unlike alkali metals, form compounds pronounced with covalent character when other members predominantly form ionic compounds. In fact, their behavior is similar to second element of following group, that is, lithium is similar to magnesium and beryllium is similar to aluminium, and this type of similarity is commonly referred as diagonal relationship in the periodic properties. The anomalous behavior is attributed to their small size, large charge by radius ratio and high electronegativity of the elements. In addition to this, first member of the group has only 4 valence orbitals, that is 2s and 2p, available for bonding, whereas the second member of the group have 9 valence orbitals available for bonding. As a consequence of this, the maximum covalent of first member of each group is 4. For example, boron can only form BF4, whereas other elements such as aluminium can form AlF6. Furthermore, the first member of p block elements display greater ability to form p pi multiple bond to itself and to other second period elements compared to the subsequent members of same group. Now let us look how periodic trends and chemical reactivity are associated. By now you may know that periodicity is related to electronic configuration, that is, all chemical and physical properties are manifestation of the electronic configuration of elements. The atomic and ionic radii, as we know, generally decrease in a period from left to right. As a consequence, the ionization enthalpies generally increase as an electron gain enthalpy become more negative across a period. This results into high chemical reactivity at the two extremes and lowest in the center. Thus, the metallic character of an element which is highest at the extremely left decreases and non-metallic character increases while moving from left to right across the period. Elements on the two extreme period easily form oxides. The normal oxide formed by the elements on the extreme left is most basic, for example Na2O, whereas the formed by elements on the extreme right is the most acidic, for example Cl2O7. Oxide of elements in the center are ambiotteric, for example CO2, NO, N2O. Ambiotteric oxides behave as acidic with bases and bases with acidic, while neutral oxides have no acidic or basic properties. The change in atomic radius of transition metals is much smaller as compared to those of representative elements across the period. The change in atomic radii is still intermediate ionization enthalpies. As a consequence, the change in atomic radii of transition metals is much smaller as compared to those of representative elements across the period. The change in atomic radii is still smaller among inner transition metals. They have intermediate ionization enthalpies. As a consequence, they are less electropositive than group 1 and 2 metals. In a group, the increase in atomic and ionization radii with increase in atomic number generally results in gradual decrease in ionization enthalpies and a regular decrease in electron gain enthalpies. Thus, down the group, the metallic character increases and non-metallic character decreases. I hope you like this video. If you need notification of future updates, please subscribe to the channel so that when I upload the next video, you get notification. Also, if you want to help your friends, you can share this video with them.